So module 17E, this module isn't very long, but it's quite important for what's to come, not only in Chem 2, but really in organic chemistry. In this module, I want you to be able to identify Lewis acids and bases, describe adduct formation, a Lewis acid-base adduct, use arrows to show movement of electron pairs during acid-base reactions, and you should be able to utilize your prior knowledge of Lewis dot structures. So first, let's define again what our acids are. We know we have Arrhenius, which is the definition we basically used in Chem 1. An Arrhenius acid forms or produces H3O plus in solution, or hydronium ion. An Arrhenius base produces hydroxide. So those definitions are great definitions and they work for a lot of the systems we have, but they aren't always completely efficient in what we need. And so we need to think about other systems and other definitions, which is where Bronsted-Lowry and Lewis acid-based definitions come into play. So we've spent some time in this chapter talking about Bronsted-Lowry. So let's remember our Bronsted-Lowry. Bronsted-Lowry acid is called a proton donor. A Bronsted-Lowry base is called a proton acceptor. And this is where we saw this concept of a conjugate acid, conjugate base coming into play. That concept is still vital for our understanding of acids and bases, and we're going to actually use that to help predict the strength of acids in the very next module. But kind of deep delving off of the Bronsted-Lowry definition is our Lewis definitions. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. So let's go back to some more simple reactions. Let's go back to ammonia. So we've got our NH3 and hydrochloric acid. If this was allowed to react, we would expect a full reaction to happen. It is a weak acid and strong base that's going to go to completion. And we would have our original ammonia, but we would see that this ammonia had picked up a proton from the HCl. And left over, we would have a chloride ion. Now, let's think about this with the actual electrons here holding this molecule together. What's happened here is ammonia acted as a Lewis base. It donated this pair of electrons to form that bond with hydrogen. HCl acted as a Lewis acid. The chloride ions accepted this pair of electrons when the hydrogen left. So it still follows a Lewis-Bronsted-Lowry acid-base definition. The NH3 is still accepting a proton, forming a conjugate acid of NH4 or ammonium. HCl is still donating a proton, forming Cl- or our conjugate base. But it's also following our Lewis acid-base definitions, where this donates electron pair, and this accepts an electron pair. So sometimes you need to see it from the perspective of the electrons, and the electron perspective is actually quite vital for your understanding when you get to organic chemistry. So we need you to be able to see this. But not only do we need to understand where these electrons are going, we often describe the movement of the electrons with arrows. We call it arrow pushing. or the electron flow in a reaction. So if you can follow the electrons in a reaction, you should be able to predict the products of a reaction. And so we need to get comfortable with arrow pushing concept. So for arrow pushing, what do we do? Well, first, here's the general rules you're going to follow. Always start the base of your arrow at an electron pair. Remember, an electron pair can be a lone pair or a bonded pair. So again, what do I mean by that? This is a lone pair. This is a bonded pair. It can start at your lone pair or your bonded pair. Draw your arrow from the electron pair to point towards its destination, which will be a more positive atom. Use your Gen Chem knowledge of Bronsted-Lowry behavior to determine the reaction. You will learn more concepts in organic chemistry for more advanced reactions. But we need you to get comfortable with this first. So let's look at ammonia reacting with water. We know that by definition, ammonia is a base. It forms ammonium. And this is its conjugate acid. In this situation, water is acting as an acid because it's going to donate a proton. And this is its conjugate base. Because OH- could accept a proton. We also can do this by Lewis definitions. We can say that this is a Lewis base because it donates an electron pair to form this bond. And we can say this is a Lewis acid because the oxygen accepts this electron pair when the proton is removed. So let's look at our arrows. The reaction here, the arrows are going to start out from our ammonia and they're going to go towards our hydrogen. That represents the formation of this bond. Now, there's a bonding pair between the hydrogen and oxygen. Those electrons are left behind on the oxygen. So we draw an arrow from the bond to the oxygen. And I know that's kind of wonky to draw. But the better you can show it coming from that bond to the oxygen itself. Okay, so that's supposed to represent it's going from that lone pair to the oxygen. That's forming the lone pair here. Or from that bonded pair to the oxygen. That's forming the lone pair here. What about methylamine? This is called methylamine because I've got a methyl group right here. And it's got the nitrogen, so it's methylamine. Methylamine, lone pair to that hydrogen. Electrons in that bonded pair left behind on that oxygen. So this is representing the formation of this bond and then the lone pair being left behind. I have a lot of extra compounds. This happens with amines all the time. I have a lot of these drawn out for you guys to practice in the additional practice sheets. I recommend you practice these because you are responsible for showing the arrow pushing and the products that are formed. We also have arrow pushing to form Lewis adduct. What is a Lewis adduct? A Lewis adduct is a Lewis acid base reaction product where you have the Lewis acid plus the Lewis base in one product. There's no what we call leaving group. Nothing is left over. Both the acid and the base are part of your final product. Leaving group is a concept we use a lot in organic chemistry. A leaving group here would be your hydroxides. These are your leaving groups. They're the leftovers. Here, we don't have a leaving group. Everything that went in is part of our final product. That is called a Lewis adduct, a Lewis acid-base adduct. If we see here, we've got aluminum chloride. We still got aluminum chloride. We've got ammonia. We still have ammonia. We've got this ether. We still have this ether. We have BCl3. We still have BCl3. So everything that went in is part of the product. That is an adduct. We can still draw the arrows here. They go from the electron pair to a more positive atom, and a bond is formed. From an electron pair to a more positive atom, and a bond is formed. And these will actually also form what we call acid anhydrides. You will use acid anhydrides more in organic chemistry. You'll see them there. But again, these reactions are happening all around us. For example, carbon dioxide is readily absorbed into water to form carbonic acid. So carbon dioxide and water, remember carbonic acid, and a series of reactions can be forming here. But how does this actually work? Well, if I have water and carbon dioxide, we see here that, remember, water has a lone pair on it. So that lone pair on the oxygen from water will go attack the carbon atom. Carbon and CO2 already has 4 bonds. Carbon cannot have more than 4 bonds. It's in the N=2 energy level, which means it is locked in with no more than 8 valence electrons. It doesn't have space for them. So when oxygen goes and forms a bond to that carbon, one of these bonds that's forming this double bond between carbon, so one of its pi bond basically is destroyed, and those electrons go up to the oxygen itself. We have this intermediate where this oxygen atom now has a -1 formal charge, and the oxygen on our water atom, or water, the oxygen in our water molecule has a positive formal charge, +1 formal charge, because right now it has 3 bonds and 1 lone pair. This lone pair from this oxygen that has a -1 charge is going to go grab one of those hydrogens from the water. The electrons that are bonding that hydrogen to the oxygen are going to be left behind on the oxygen originally from the water, and we form carbonic acid. So here, this bond has been formed, a pi bond here has been broken, and this bond has been formed, forming carbonic acid. You are responsible for being able to draw these out and understand this process and where the electrons are traveling. So again, they can come from a lone pair or a bonded pair, but it's going from the electrons to the more positive atom.